large polar ice caps and the polar layer deposits. But as you go towards lower latitudes, ice is not at the surface, but it's found in the ground, potentially within centimeters of the surface. And theory suggested that this ice should be present down to somewhere in the mid-latitudes between around 40 or 50 degrees north. And we found a new way to probe this a few years ago as we began detecting new impacts on the surface. With a record of images stretching back for several decades, it's possible to compare new and old images and detect impacts. And the way this is generally done is with the Mars Reconnaissance Orbiter Context Camera. Large dark spots are often found. And what these are is the blast pattern that you can see around a crater. You can see in this image here, there's a small crater surrounded by ice at the center, and then a larger dark pattern. And so several hundred of these have now been found, comparing images from this long record that we have. And some of them do excavate ground ice, and so we can use these to map out ice in the subsurface where it can't be seen on the surface. What you can see here is a map of the distribution of these new craters. The red points show new craters that didn't excavate ice, and the blue points show where the ice was seen. You can see also that these craters are mainly found in the light-toned areas of this map. This shows the albedo of Mars, and that's because that's where these dark blast patterns are most easily seen. It's not that craters preferentially form there, it's that they're most easily detected there. What you can also see is that as you go towards higher latitudes, from about 40 degrees latitude north and up, these impacts tend to expose ice. And there's a couple in the southern hemisphere as well at very high latitudes. We found now ice in some of these new craters as close to the equator as 39 degrees north. And so this lets us do a couple of things. The first interesting thing about this ice is that it appears to be quite clean. These craters stay icy as we look at them over and over again with images from pyrites for months or even years. And the ice must be sublimating during that time. It gets warm in the summer, enough for the ice to sublimate. And so that suggests that this is relatively clean ice that's being excavated, not just ice filling in the spaces in the dirt. The other interesting thing about this is that the distribution of ice on Mars depends on the water vapor in the atmosphere. If there's more water vapor in the atmosphere, then ice will be deposited in the ground closer and closer to the equator. So mapping the distribution of these craters lets us understand how much water has been in the atmosphere of Mars near the surface over the timescale of centuries to thousands of years that it takes for the ice to adjust. And so using models of the theory of this, we can estimate what kind of water content is required to match the distribution of the craters that we see. And it turns out that the amount of water vapor that we estimate near the surface is, over this thousands of year time scale, is somewhat higher than we would guess from estimates of the current amount of water vapor in the atmosphere. That could mean that the current measurements of the water vapor have it concentrated very near the surface, at least some of it, or it could be that the average over thousands of years is somewhat higher than the present. So these craters are giving us a window and a linkage from current geomorphology and impacts to climate and its status over thousands of years. But we've also learned quite a bit about the recent Martian climate, and I'll hand it over to Bob Haverly to talk more about that.
All right, thank you, Colin. For the past 16 years, we've had 9 spacecraft at Mars. 5 of them are still operating. Some of these spacecraft were landers, some were rovers, and some were orbiters, but all of them were equipped with payloads that can address the climate system during the present day. And I've been asked to just briefly discuss the dynamic nature of that climate system, which I generally define in terms of the seasonal cycles of dust, water, and carbon dioxide. And these cycles are linked together through the general circulation, global circulation patterns. And we know there are seasonal cycles because we can measure the amount of water, CO2, and dust in the atmosphere, and they vary globally with season. So that means the atmosphere is exchanging material with the surface. So atmosphere-surface interactions are very important to this process. So let me go to the next slide here and talk about the dust cycle. The dust cycle is actually the most complicated of the three cycles I mentioned. And it's complicated because we don't really completely understand how dust gets into the atmosphere. We do know, however, that there are a variety of different storms that lift that dust in the atmosphere. And you can see an example of each of these storms on this slide. They range in scale from very small scale systems, dust devils, as Al showed you earlier, to very large scale storms that can actually spread dust over the entire planet to altitudes in excess of 40 or 50 kilometers. These are the so-called global dust storms. So this long-term set of observations has allowed us to begin to characterize the nature of these storms. However, we don't really completely understand the mechanisms that lead to having different kinds of storms, and in particular the global scale dust storms. They don't seem to occur every year. For example, in the next slide, there are a couple of images here of two what are called regional storms at this point. The one on the left was taken by the Viking Orbiter 2 back in 1977, and you can see a very nice, well-defined sort of ribbon of dust. The dust is relatively confined at this time, but only a few days later, that dust storm became a global event and spread dust all over the planet. The storm that you see on the right was recently imaged by MRO just last year at this time. It too began as a regional storm of about the same scale as the one on the left, but it did not go global. So while we have learned a lot about the morphology and the structure and the variability of these dust storms, we really don't completely understand why some of them become global and others do not. Let me now turn to the water cycle. Again, we know that there's a water cycle because we can measure water vapor in the atmosphere, and it varies seasonally and latitudinally. And one of the major questions about the water cycle is, well, what are the sources and sinks for that water? And again, from this long-term set of observations, we now know that the major source for atmospheric water is water ice at the North Pole. It's something that we call the residual North Polar Cap. So every year CO2 condenses at the poles, but eventually sublimates away during spring and summer, and at the North Pole it reveals a water ice cap, which heats up and provides water to the atmosphere. The interesting thing is that the South Pole also has a residual cap, but it's not water, it's actually CO2, dry ice, and it survives all year long. And that cap will act as a sink for water. So we have a source at the North Pole and a sink at the South. In addition to those sources, we also have seasonal ice deposits, and we also have potentially water exchanging with the regolith. So we've learned a lot about sources and sinks. What we don't know today is whether these sources and sinks are gaining on a net annual basis or not. And this question is a very important question when you're interested in long-term climate change of the nature that Colin was describing. We would like to know how the ice that they're finding at these lower latitudes actually got there. And so by studying the present-day water cycle, we hope to be able to answer those questions in the future. And finally, let me turn to the CO2 cycle. I think everybody is familiar with the familiar waxing and waning of the polar caps on Mars. This is because it gets cold enough in the polar region for CO2, the main atmospheric constituent, to condense on the surface. So during the winter, the polar caps grow and they pull mass out of the atmosphere. And then the opposite occurs during spring and summer when the caps are sublimated. So the mass of the atmosphere is changing on a seasonal basis because of this cycle. And we can actually see that signature in pressure data. Pressure is a very good measure of the mass per unit area in a column of atmosphere. And what is shown in this slide here are pressure measurements from the Viking landers, which was taken in the 1970s, and then the more recent measurements from MSL during the past year. This period of time shown on this graph covers about 3/4 of a Martian year, beginning in northern summer, southern winter. So that's the minimum. The minimum in that curve here corresponds to when the south seasonal cap is at its maximum extent. And then as the season progresses, the cap retreats and puts mass back in the atmosphere, and you can see the pressures rise. What we're hoping to learn from this pressure data are many things about the atmosphere today, but we're also interested in potential climate change. If I can have the next slide. As Al mentioned in his talk, there are these pits that are changing in morphology in the south residual cap, and there are other observations that show scarps retreating, and there has been a suggestion that the south polar residual cap may actually be disappearing steadily year after year. If that is the case, and if the disappearing mass is going into the atmosphere, we should see a signal of that in the pressure data. So here's another really good point about the value of long-term measurements. Because we had pressure measurements during Viking, and now we have pressure measurements during MSL, a period of about 19 Mars years, we can begin to assess the potential that the South Polar Cap is actually disappearing. So in conclusion, I think there's a real value in having long-term measurements, and we're looking very much forward to continued measurements to help us characterize and understand the dynamic nature of the Martian climate system.
Okay, we'll open up for questions now. Are there any questions from the floor?
Hi, Irene Fox with Discovery Channel and Reuters. How far beneath the surface do you think the ice is at the 39-degree inclination that's exposed by the impact craters?
It should be within tens of centimeters, a meter or so at most. These craters that are excavating it are, the largest is over 20 meters in diameter, but that's at high latitude, so these don't dig down all that far. It's generally close to the surface.
Thanks. And is there any data from any of the orbiters as to the contents of that ice?
It's water ice, and what's somewhat surprising is that because it stays relatively bright so long, it seems to be relatively clean, relatively pure water ice.
Other questions? Any questions from the chat?
Camille Carlisle with Sky and Telescope. Why would the RSLs prefer the least dusty locations? And also, how much does the atmospheric pressure on Earth change seasonally compared to the seasonal change